Thank you. The pleasure is mine. I'm happy to be here. Can everybody hear me? Everything's working okay? Excellent. Awesome. Thank you. Hi everybody. I'm Chelsea Troy, as you just heard. Chelsea, like the neighborhood New York, Troy, like Helen of Troy. I am a programmer and an educator, as you heard. And today we're going to talk about what counts as a programming language. So, before I begin, I want to warn you that programming languages aren't really the point of this talk. They were definitely originally going to be the point, but as I dove into researching programming languages and comparing the ones that I've written in for this talk, I found a theme that I think you'll find applicable inside and outside of programming languages. My hope is that it'll be useful to you as engineers regardless of the language you write. So we'll still center programming languages in our discussion, but this is really a talk about assumed context. Throughout the talk, we'll explore this theme within the exemplary domain of programming languages. And we'll get to what that means, don't worry. But before we do, I'd like to start this talk the way you'd expect a talk about what counts as a programming language to start, which is, of course, with a cursory literature review on the titular question, what counts as a programming language? So I truly did the bare minimum here, and I Googled the question. So what you see here on this slide are some of the most inclusive answers that I found among the results of that search. For example, according to Code Academy, a programming language comprises the tools we use to write instructions for computers to follow. We have a similar definition from Wikipedia. A programming language is a formal language comprising a set of instructions that produce various kinds of output. Now, these both sound like fairly inclusive definitions, right? Especially the latter one. It includes almost anything. That can include even natural languages. But in practice, the discussion about what counts as a programming language is not such an inclusive one. Professional programmers frequently introduce a number of possible heuristics for determining whether something is a programming language or not. And in having this discussion with professional programmers, I've heard a few different questions come up that might help us to determine what counts as a programming language in practice. First, does it have to be Turing complete? Does it have to be able to solve any of the problems that a Turing machine might be able to solve? In practice, that would mean it has conditionals that allow for branch logic and so on. So I've heard Turing completeness used to rule out stuff like markdown languages as programming languages, but we'll get there later. Let's look at some of these other questions. So, does it have to be usable for solving a specific kind of problem? We count the things as programming languages that we use to solve what we categorize as programming problems. We often count the development of applications that take input from end users as programming problems, for example. We count algorithmic implementation as a programming problem. When it comes to app layout or design, we usually don't count those as programming problems, and we don't count the tools we use to perform them as programming languages. But then there are fuzzy cases, right? Data structure usage in class design, things like, for example, inheritance, often get categorized as programming problems right up until we're talking about CSS, cascading style sheets. They have classes and mix-ins, but despite the fact that CSS employs inheritance and class design principles, it doesn't get universal recognition as a programming language. So let's look at the next question. We talked about whether a tool has to be usable for solving a specific kind of problem. Does it have to actually be used for solving that problem? So, for example, when we're teaching people programming languages, we often do so by asking people to implement a game like tic-tac-toe on the command line. That sort of problem is useful for teaching people how to write in a programming language, but we're not using the programming language for a programming problem there. We can also solve the problem implement tic-tac-toe with 4 lines and a pencil, but that doesn't count as a programming language. So, finally, does it have to have a compiler or an interpreter? Now, here's what's interesting about this question. At first glance, this one sounds like it would be the strictest one. Well, maybe, but at its core, what a compiler does is it takes a representation of data in one format and it transports it to a format that we can use for something else. It turns front-end syntax into an abstract syntax tree. But is it, and how is it, fundamentally different from translating one natural language into another, or converting CSV data into JSON format? We don't think of either of those types of translations as compiling or even transpiling, but we also don't have a clear delineation of the differences that doesn't start with differentiation and then try to backward justify it. These boundaries that we want to think of as clear and objective are far fuzzier and wispier than perhaps we'd like. Now, we've talked about some of the general questions that might come up after work around the water cooler about what counts as a programming language. The more specific questions might include something like this. Is a markup language a programming language? Maybe HTML or Markdown or XML or JSON, the ways that we typically represent data for programming languages to consume. Now, I'm not going to claim there's a consensus because there isn't. But in general, programmers will say that these things don't count as programming languages. And when you ask 3 different programmers for the reason, they'll give you 4 to 5 different and sometimes conflicting reasons. I'm not necessarily disagreeing with the delineation, and I'm going to get to why not later, but I just can't ignore this any longer, and I have to state it for the record. I do find it suspicious that these dubious claims about what counts or doesn't count as a programming language move and change over time to shadow almost exactly whatever it is that the dominant demographic is willing and able to write at that time. Once upon a time, programming wasn't considered an intellectual task. It was considered quote-unquote women's work, and early NASA missions had employed women in a role literally called computer to calculate mission trajectories. Women repaired the early ENIAC machine, and although historical grounds for the claim that Grace Hopper coined the term bug are kind of dubious, she is, in fact, of the demographic that would have been clearing moths out of the wires at the time. What a difference 50 years makes, huh? I highly recommend, by the way, Robin Hauser Reynolds or Mar Hicks's work for more on that, but it's a topic for a different talk than this one, so I'll move on. How about a query language? Is that a programming language? Take SQL. That's a query language that we use for relationally oriented databases. Or Cypher. That's a query language that we use for graph databases. Once again, no consensus on the question, but generally, programmers tend to be more willing to think of query languages as programming languages compared to markup languages. Once again, though, ask 3 programmers why, and you get an amalgam of, at best, orthogonal answers. So let's take a step back. What are we trying to describe? Why does it matter to us what counts as a programming language? What are we trying to figure out here? Because we said programming languages, but maybe some context is missing here. Now, by context, what I mean is the descriptors that characterize our specific situation. So the place where I grew up is a context. The city that I live in is a context. The industry that I work in is a context. The type of software that I work on is a context. The language that I learned as I was growing up is a context. And it's important for us to recognize those descriptors because they inform and characterize our perspective. Those things about me influence how I see everything. And to me, the way that I see things can be difficult to separate from the truth because it's what I see as the truth. Perspective is especially important in software engineering, and here's why. Computer science is not like biology or astronomy or geology or physics or fluid dynamics because it is not a natural science with properties that we spend time studying and did not create. Computer science is entirely human-made. We built computers, which means that at every step from its inception, our perspectives played a role. There is no piece of computer science or software engineering that is devoid of context, because context informs the perspectives on which all of it was built. And here's how that can bite us. When we are unaware of the context that we're in, we can accidentally mistake our specific case, our perspective, with an imaginary general case that applies to everyone. An imaginary truth. Before we go back to programming languages, I want to explore this idea because I get that it's a little abstract. So we're going to look at some context-specific examples to make this clear. So I want you to think about this statement for a second. Generally, it is better to optimize our code for legibility than for speed. Do you agree with that statement? Generally, it's better to optimize our code for legibility than for speed. You see the word there underlined? Generally. What do we mean by generally? It turns out there is context lost here in generally. Generally here means in most cases, but it doesn't answer the question, in which cases? Generally, it's better to optimize our code for legibility than for speed. Maybe when we're writing end-user client applications, it's better to optimize for legibility than for speed. Maybe when we're writing open source applications that rely on multiple developers across the globe communicating with each other asynchronously such that later developers need to be able to understand and maintain the code that the first developer wrote, sure, maybe then it's better to optimize for legibility than for speed. Over the past 2 years, I started implementing compilers and interpreters. So for the first one, I was following the book Crafting Interpreters by Bob Nystrom. I highly recommend it. It's available for free online, or you can get a physical copy. I wasn't paid to say this. It's just a really good book. But as I went through the beginning of the book, during the lexing portion, where we identify tokens in the text of the source code, I came across this giant case statement that switched on all the tokens, every token that you can think of. And I decided that I could do a better job than that of expressing the hierarchy of tokens in my compiler. So I refactored that code into a series of conditionals, and I thought it read so cleanly, and I felt so smart. And I reached out to Bob and I asked him, hey, out of curiosity, why is it done with a case statement when other solutions might be more legible? And he responded to me. He was very nice. He agreed that the tiered conditionals added legibility. But the truth is that when you're writing a programming language, it's extremely important that the thing be fast, because you don't have to worry about the speed of looping over 14 keys and values in your Ruby app or your Python app or your Java app, because the people who wrote the compilers and interpreters of those languages made them fast enough to give client developers the luxury of optimizing for legibility. They optimized for speed so that we don't have to do it in end-user client application development. Let's talk about another example of the context hiding in generally. Generally, composition is preferable to inheritance. Have you heard this saying before? What do we mean by it? Once again, we have this word, generally, that doesn't do much to help us differentiate the common case from its exceptions. So I teach a class at the University of Chicago called Mobile Software Development, and we learn Android and iOS. So both of those frameworks rely heavily on having the client developer inherit from classes provided by the framework. It ends up making those classes tough to subject to automated unit tests because Android and iOS handle the instantiation of those classes for you. And so you got to use various hacks to instantiate them yourself for testing purposes. You have to go around the framework to test it. Why do it that way? It makes testing so hard. Well, it turns out that when you're trying to make complicated stuff happen on a device the size of my palm, it's really important to conserve memory, which means it's really important to conserve the number of objects in memory at a given time. And it's a lot for a developer to think about. And it's likely an accessibility hurdle for client application developers. In order to take some of the load off of client developers, the folks implementing the Android and iOS frameworks wrote that behavior into prefabricated classes with convenient hook methods for client developers to put their own code. They're referred to as lifecycle methods. Once again, end user application developers have the luxury of preferring composition to inheritance because those framework designers used inheritance to solve problems that end user app developers no longer have to think about. And that brings us to the question, what does generally mean? I mean, we agreed earlier that it means in most cases, but which cases? Now, I do want to add one caveat here, which is that I understand that when someone is new to learning programming, we use the word generally to keep things simple. We don't want to expose them to all the nuances and special use cases right away. That's an impractically complicated, not to mention intimidating introduction to the field. No one starts by writing a compiler or the Android framework after all, so what does it matter? I agree that it makes sense to start simple. But when we reach the point in our own technical advancement where we are responsible for teaching other people statements that start with generally, at that point, I believe we are responsible for knowing what that generally means. We are responsible to know which cases we are talking about when we say generally. So now let's return to the topic of programming languages. Ruby, Python, Java, Kotlin, JavaScript, etc. are considered to be general programming languages. There's that word again, general. General programming languages, we say, differ from domain-specific languages like Cypher, the aforementioned query language for graph databases, or RSpec, a domain-specific language for writing automated tests in Ruby, or regexes, a domain-specific language for describing patterns within text. By the way, if you're interested in regexes, Betsy Habel has an excellent talk on the design of regexes and why they're so pervasive. You can find it on YouTube. Highly recommend. Once again, not paid to say this. It's free. It's just a good talk. But the point is that we have this idea of a general programming language that transcends what we expect from a language that is merely domain specific. Here's the thing, though. I'm not sure what we mean by general here. What if the general case is, in fact, specific to a domain, and we only think it's general instead of domain specific because we consider its domain to be the default one? Much like the way we call a t-shirt a unisex t-shirt, even though it's just a men's t-shirt that we sell to everybody. Then we have women's t-shirts that drew the short straw and ended up as a special case, and that rarely gets provided in the conference swag. Really, we don't have a general case there. Like, we have two specific cases, and one of them gets treated as the default. So what if we do that with programming languages too? So Brett Victor talks about this on his blog. It's called Worry Dream. I recommend taking a look. He talks about the default domain for programming languages. What do we mean when we say a general programming language? Maybe we're actually talking about a domain-specific programming language, but the default domain is end-user applications where the user can change something. We're not talking about static web pages because the programming community has decided that the HTML and CSS we would use to write that aren't programming languages, I guess. Here's the thing. This end-user application domain, maybe it's not really the default domain. Maybe it's just the one that's received the most attention. Maybe we should be paying attention to other domains just as much. Now, why has end-user application development specifically received the most attention? That might be a topic for another talk, but for now, let's entertain the idea that it's a domain-specific case, and that there are other domain-specific cases that it would make sense for us as programmers to pay more attention to. Take Alloy, for example. This is a domain-specific programming language. The domain in this case is structural verification. Alloy helps us check our assumptions about how our domain models will work given the constraints that we intend to impose on how they work and interact with one another. It uses a set solver to show us configurations of our domain models that would satisfy our constraints, and it can specifically identify configurations that we think shouldn't happen, but that our constraints allow. Alloy, in another domain-specific language called TLA+, can be used to identify domain model issues that you otherwise wouldn't identify as a defect in the system until 17 steps down the line when some complicated data corruption has happened. But we're not prone to using Alloy and TLA+. We use general programming languages rather than domain-specific ones. So, instead of verifying our domain model ahead of time to eliminate those defects up front, we instead write an app, get 6 months down the road with 60,000 lines of code, find a weird bug that we can't figure out how to solve, write a ticket to investigate it, put a bunch of angry face emojis in the description on the ticket, come back every month or so when the issue resurfaces, but never ultimately figure it out. That's not better, right? What if we were prepared to identify those situations in which general programming language wisdom fails us and ask what we can learn from domain-specific solutions like structural verification languages? Let's look at another example. This is Modelica. There is a similar programming language called Simulex. These are domain-specific programming languages for modeling physical systems, used frequently by mechanical engineers. A big client is Ford, General Motors, designing cars. These types of programming languages are extremely effective at helping to determine how complex mechanical systems need to work together. Getting complex systems to work together is another thing that the general programming language community generally categorizes as difficult, right? In most cases, categorizes as difficult. What could we learn about how to perform that task effectively from the designs of these two languages? How could end-user application development benefit from importing those lessons into a new domain? Let's do one more example. And I've saved my favorite for last. Cypher. We've already talked about Cypher twice, but I keep bringing it up because I think it's a fantastic query language. I love writing Cypher. My favorite thing about it is that a query in Cypher often looks like a little diagram of exactly what you're trying to get out of the database. These round parentheses that you see in the example, they enclose the models represented in our query, and the square brackets indicate the relationships between those models. You can even see that there's an arrow demonstrating the directionality of those relationships. So the query draws a little picture for you of what you're trying to do. And I think that's not just a cute language feature. It's significant. I think it's significant because so far in my tenure as a programmer, I have seen at least 3 attempts to make a diagrammatic development environment that allows developers to write a general programming language by somehow drawing diagrams or pictures of what they want the system to do. All 3 of those efforts that I have seen have failed. And so I wonder if we are willing to promote query languages like Cypher to the level of importance that we give general programming languages. What could we learn about how to succeed with the diagrammatic representations of program logic that we have been trying so hard to make? The point is that other domains exist, and paying attention to them can make us better at this programming thing. I want to know what we can learn as engineers from languages that we think of as domain specific. I think the only way we can do that is if we recognize them as siblings rather than subordinate to the so-called general programming languages, because it turns out those languages also have their specific domain. We talked about this question earlier. What separates converting CSVs into JSON format from parsing a high-level programming languages to an abstract syntax tree? One operation might be more complicated than the other, maybe, but it's difficult to come up with an objective answer as to what makes one of these processes subordinate to another. And even if we could do that with confidence, I'm not convinced that it's a particularly productive conversation to have. Rather, there may be more value in learning to identify contexts and share information across contexts than in formalizing our understanding of the differences between domain-specific languages and 2 separate domains. It doesn't matter what counts as a programming language. What matters is, where can we find contexts where there might be transferable knowledge? You and I swim in a sea of context. And the thing about context is, it's very easy to not realize it's there, to take it as a default, as a given. But it's worth learning to identify, because by identifying it, you can access a deeper and better connected understanding of programming languages. And you know what? Maybe anything, but I'll stick to what I know. By learning to find the invisible context hidden in general statements. So how do we do that? Well, I have a couple ideas. I'll share 4 of them with you. So, first of all, I recommend asking yourself a question. What principles or ideas or best practices do you think of as always right or generally right? What strikes you as right or true? I recommend pulling out a notebook, write down 2 or 3 of these. You don't need more than that for now. 2 or 3 will already give you a ton of practice identifying context that you didn't realize was there. All right. So once you have those written down, let's look for the context in which this is the case. look for the water around you. Ask, if this thing is generally true, what do I mean by generally? If it's true in most cases, then what exactly are those cases where it is true? Once you positively identified cases where that thing is true, it's time to look for patterns. So suppose you've seen this to be true in X, Y, and Z cases. What's similar about X, Y, and Z? For example, were they all end user applications? Were they all for a specific market or a specific type of client? Did they all solve a similar problem? What did they have in common? That's a really strong clue as to what the context is that most heavily informs your perspective. Write that down. That's important to keep in mind. Now, maybe you can see where we're going with this and guess what the next step will be. Ready? Now, it's time to step outside that perspective that we've identified. And for this specific truth, you can do that by looking for cases where this truth isn't true. What are the exceptions? Under what circumstances might this truth no longer apply? Go looking for applications that don't have the thing in common that X, Y, and Z had in common. I'm asking you to go looking for contexts that are different from yours to better understand why your best practices work in your context. Nothing demonstrates why something works better than an example of where it doesn't. So, doing this also gives you a better understanding of how your practices work and when they work. Finally, and this is the thing I'd love to see us do that's going to allow us to draw wisdom from Alloy and TLA Plus and Modelica and Simulex and Cypher. Go looking for context similar to yours. What can your tried and true approaches contribute to this similar context? What can you learn from the similar context about what new things to try in your own context? Because when we learn to humble ourselves and understand our perspective and the fact that it differs from a universal truth, that gives us an opportunity to capitalize on other perspectives to build a better model of what the truth is and how we can find solutions for the problems that we face. Learning to see our own context and understand and compare other contexts will help us open doors as solutioneers that previously we couldn't not only open, but we couldn't even see. So I hope that some of those steps end up proving useful to some of y'all, and I think I'd like to yield the remainder of my time to questions. We're doing questions, right?
We certainly are. As I leap for the unmute button fairly unsuccessfully initially. Thank you very much, Chelsea. I'm kind of thinking of our closing talk yesterday. We had a story from Daniel Turhurst North about how he took his best practices into a client and it all turned horribly, horribly pear-shaped because the context that he was expecting was not the context that was there. So there you go. Universal experience.
We planned it. We planned it that way.
That's it. It's all a theme. Right. So everybody jump in and pop your questions into the Q&A. I have a question, which is, do you kind of have a story or like an aha moment when you first kind of came to all these ideas, which, you know, where you first realized that you needed to kind of bring together all these, you know, a lot of languages.
I do. I've written, yeah. So I've written a number of different programming languages to prod. And one of the things that has always kind of bugged me about the programming community is the way that we want to put this like hierarchical significance chart together about what's the hardest and the most technical and the most important and all those kinds of things. And generally, the reason that's given for why we don't want to do that is that it's like not very nice which is of course true, and it discounts a lot of very important contributions that people have made. But it's also just dead inaccurate. It's also just like wrong. It's like it's not only wrong in like an ethically wrong state, it's just like inaccurate, and it ends up making us worse at our jobs. It causes us to miss really valuable insights. And I think the thing that made me start to realize this, it took me a much longer time to sort of put these things together in a coherent way that I could talk to other people about. But I noticed pretty quickly, like I was, I don't know if these are the terms, but I wrote one language and then I wrote two languages and then I was a triglot and then I knew four and then I was working on my fifth one. And what I realized was that often when my team was stuck on a problem in one language, I could contribute to getting us unstuck by taking ideas that I had learned from a different programming language community and applying them to the one that I was working in. Every programming language has also kind of a culture around it. Rubyists have a culture. Pythonistas have a culture. Android developers have a cult. That's not a language, but that framework, there's like a culture around it, you know? And within those cultures, certain ideas get their primacy. The culture among Haskell programmers is significantly different from the culture among Python programmers. But the ideas that get that primacy, because the ideas that get that primacy differ, it when we're mired in one programming language community, it can cause us to miss opportunities that another programming language community might alight upon. And one thing that makes it very hard to learn from other communities is the belief that our community is somehow superior to another one or somehow has nothing to learn from another one. So I think that was maybe one of the important pieces that I realized. The other important piece that I realized happened not on a programming language level, but I think on an interpersonal level. I started to realize that the best solutions to technical problems or to business problems came out of disagreement. Because inevitably, if everybody agreed on what we were going to do, there ended up being some shark in the water that nobody saw. And disagreement happens because somebody sees the shark that the other people do not see. And although it can be uncomfortable, realizing that made me value the diversity of perspectives, not just from an ideological standpoint, but rather from a practical one, because I had seen situations where that diversity of perspectives was critical to making something work. Not for some highfalutin reason, but because actually there was a big danger that we would not have seen if it weren't for this person who had a different perspective, who identified it, and they totally called it, and they were right. And we were very lucky that we had listened to them. And I think that that ends up being true in a technical capacity as well a lot of times. And I think that in general, programming communities, and maybe it's because a lot of us grew up like nerdy introverts or whatever you want to say. I don't think that's necessarily true. I try not to lean into that stereotype. But it's a relatively conflict avoidant culture, tech culture. We try to avoid arguing. I think it's not even necessarily isolated to tech. I think people want to avoid an argument, and we don't learn nearly as much as we should about how to capitalize on alternate perspectives and value disagreement because of what it does for us, and then work through disagreement in a way that avoids conflict and gets to the root of what somebody's seeing that somebody else doesn't. I think if we cultivated that skill as a technical community, we would build much more technically sound solutions. And I think that that's also true at the programming language level, coming in with the ability to capitalize on different experiences and the ability to see different contexts ends up making a solution in any language more sound, because there isn't going to be like one, there is less likely to be one perspective or one danger or one risk that gets completely missed. Hi.
Oh, and there's
Ozzy
the
is
cat.
here. Hello.
Excellent. Good of you to join us, Ozzy.
Ozzy, what do you have to say?
Arguments tend to be unproductive as well. Side-eye to Twitter, just saying. Okay, next question is from Richard. who says, in my own experience, language choice has been most influenced by market availability and, quote, used before, unquote, syndrome. How much should domain and context also influence those choices?
Yes, so this is a good question. I think the elephant in the room that we don't often talk about is it programming language and framework choices. Give me your foot. There we go. Programming language and framework choices. One of the big factors in that choice, in my experience, is often what the team is most familiar with or what the decision maker is most familiar with. And we avoid talking about that because we feel like it's taboo, but I actually think it's not necessarily a bad way to make a choice. The reason is that a lot of times we're under deadline, we need to get something done, and asking somebody to learn a new programming language in order to be able to get that thing done might not be realistic to what product is asking us for. I think if we were able to acknowledge it without the guilt that we associate with it or the shame that we get from other people about it, then we would end up being in a much more productive position when we're choosing a programming language or framework for a problem. I also think that there is value, and this can be tough to convince a business of, but I think there is value in specifically cultivating experience in multiple languages and frameworks so that when that decision is being made, the decision maker has more options or feels like they have more options. I'm a big fan of finding ways to reintroduce choice where it feels like we don't have a choice. And I think even as much power as tech has and as much leverage as tech has as an industry, I have many times as a software engineer felt like I did not have a choice or did not have a good choice in what I was trying to do. And I think that becoming familiar with more languages and more language communities is one way to start to reintroduce some of that choice. Ideally, of course, it would, we'd love to be able to choose the language that's really the best optimized for the particular problem that we're trying to solve. But even if we're not able to do that, even if we have a team that all knows one language and we're not going to be able to convince them to write something else under the deadlines that we have, it's still valuable even within that language to be able to bring some of the perspectives of other languages and to be able to say, okay, we're going to write this in, I don't know, let's say we're going to write this in Java, but we have experience from C++ and C on the team and some Python on the team and those kinds of things. And those experiences with those communities can allow us to draw from more collective wisdom within programming than we would if we were specifically ensconced in the one language community of the language that we happen to be writing on this project.
It's kind of like the whole, if all you've got's a hammer, everything looks like a nail kind of thing.
Exactly. Yes.
So let's just say from your experience, if you were to say, you know, hey, go learn some different stuff, what would you say represents a good selection of random choices that would let you become slightly better at the spectrum?
This is an excellent question. Now, I'm a person who sort of likes going and learning a little bit about these kinds of things, and so I don't know how representative my choices will be. But before I give these examples, I do want to say you don't necessarily have to become a master of other languages before you can start capitalizing on the alternate perspectives of their communities. Even knowing just a little can give you a perspective that you didn't previously have. So with Alloy, I took a workshop from Hello Wayne, which was very good. And then I wrote an Alloy spec, and then I asked him to pair with me and make it better. I actually have a blog post about this. I recorded the entire thing. I look like a total bonehead for sure, but it's fine because I don't know the language and he knows it very, very well. So of course he's able to identify all kinds of things that I can do better. It was an excellent learning experience for me, and even just that much work. And at that point, how much time had I invested? I don't know, 8 hours for his class, maybe another 8 of like reading and stuff, and then maybe 2 to 4 hours for writing the spec and pairing. So I'm by no means an expert in Alloy at that point, right? But I can already start to identify some of the opportunities that structural verification thinking might give me in thinking about what data model I'm going to use on the next application that I write. And so that's the first thing I want to say is you don't have to know all that much. I recommend Cypher just because I think it's cool. I think it's fun. I think people have fun writing it. That's kind of I like that one. In terms of languages that I use and write, I do a fair amount of like machine learning support and that kind of thing, so that'll tend to be a fair amount of Python lately. And but that having been said, when I'm teaching, my favorite programming language for teaching programming concepts right now is Swift. And the reason that I like it is, first of all, it's open source, so folks can go and find information about it, which is really cool. The second is that I think it does a decent job of operating in both imperative and functional constructs. So, whereas with something like Python, it's a little bit harder to help students understand the benefit of functional constructs because Python isn't really set up to take advantage of the benefits of functional constructs, right? And the authors of the language say this openly, like it's not a secret. So, it can be a little bit more, I have to be more contrived in the way that I introduce functional constructs to students in something like Python, and it makes it a little bit tough for them to understand the value. So my favorite is for that is Swift right now. I guess that's a few that I would pick. But honestly, whatever you're thinking about picking, I think it can still broaden your perspective. I was thinking about learning some APL a while back. This language looks very illegible if you're used to traditional programming languages, but it's based on manipulation of arrays, and it's really cool. Um, that's still on my to-do list. I'm not going to say that I'll do that. But if somebody knows, if somebody in the crowd knows APL and wants to pair with me and we can put it on YouTube, like, let me know. That'd be so fun.
Dave Thomas is semaphoring wildly and
Oh my
getting very
gosh.
excited.
Let's do it. You know how to find me. I'm Hey Chelsea Troy on Twitter. I'm at chelseatroy.com is my blog. Chelsea at chelseatroy.com is my email. I'm very findable.
Here we go. It's all happening.
Yeah.
It's interesting, you know, when you're talking about diversity. I think a lot of people, when they think about making more diverse teams, they're like antsy women's, and they kind of aren't thinking about programming language experience. So that's a very interesting slant, I think. Obviously, as well as all kinds of other diversity, there's the language side.
Well, and in fact, I think a lot of positions are specifically hiring for, this has changed. I think it's not this way as much anymore. But I think in particular, before it was very common to be like seeking a Python programmer, seeking a this programmer or that programmer. And which is once I got used to ramping myself up on programming languages, always felt like kind of an artificial barrier because I always felt like particularly a relatively experienced programmer is at most a month away from being, you know, a net addition to the team in terms of velocity in a given programming language, particularly if it's one from a relatively similar paradigm to the one that they know before. And so it seemed almost like the idea was specifically to hire for a homogeneous team in terms of language experience, which is not a thing that I recommend for the long-term health of the team, for the same reason that you can't plant the same crop in a field for 10 years and expect that it's going to keep working, or yeah, I can't think of another metaphor right now, so we're going to stick with the crop one. But
Yeah.
yeah. So.
I've seen that here too as well. A lot of companies now are hiring and they're not specifying must have X years in blah. You know, they're hiring a little bit more open-mindedly, I guess.
That's right.
Probably the right term. Yeah.
I think that's probably helpful. I wonder how much, I don't remember exactly which company it was that stepped in it, but somebody asked for X years of Swift experience and the X was like longer than Swift had been around. And nobody
that
will let
happens
them.
all the time. That happens. That's like the one recruiting joke that you hear a lot is people. Yeah, it's like unless it's the guy that invented it or the lady that invented it, you're not gonna get any applicants.
Oh my gosh.